everyone, welcome to your lesson on ocean currents. So we are moving out of our unit on freshwater and into our study of the ocean, and that will move us into our study on the atmosphere and weather. So a body of ocean water that flows from one place to another is the definition of a current. So you have the ocean, and in the ocean there's like mini little rivers all over the ocean. Those are ocean currents. The job or purpose of ocean currents, two main things: to control global climate and to cycle nutrients in the ocean. Ocean currents that move toward the poles are higher latitudes, and there's a picture in just a second to give you a visual. So the ocean currents that move toward the poles are warm because they're coming from the equator. So remember, the equator is 0 degrees latitude. So anything coming from the equator or around the equator is going to have warmer water. So it's going to take warmer water up to the poles. And then ocean currents that are moving toward the equator are cold because they're coming from the poles. Makes perfect sense. If it's coming from the poles, it's cold water. If it's coming from the equator, it's warm water. And that movement is what helps circulate different temperature water across Earth, which also helps to regulate climate. And so here's the visual for latitude. The equator is 0 degrees latitude, and it's like Earth's belt. And then as you go up or down from the equator, it goes in 10-degree increments. So if you're going above the equator, it's north, and if you're going below the equator, it's south. And then longitude's the opposite. So the prime meridian is 0 degrees longitude, and then if you go right, it's west, and left, it's east. Okay, so here is a really great diagram showing you the movement of different ocean currents across Earth. You see the blue and the red, those indicate different temperatures. The warmer is the red and the blue is the colder. And if you notice, you see the blue primarily at the poles, and it's moving towards the equator. And you see the red primarily at the equator, moving away from the equator. Some of them are moving towards, but they're circulating in such a way that allows different temperature of water to be circulated all across the Earth. So there's two different types of ocean currents that we're going to focus on. So ocean currents can either flow at the surface of the water or far below the water. And the two types are called surface currents or density currents. Density currents, a synonym for density currents, are deep ocean currents because they flow below the Earth's surface. So we're going to start with surface currents. Surface currents is the movement of water that flows horizontally on the surface. So when the wind blows across the ocean surface, it creates a current on the surface. It's like if you blow across the top of a glass of water, it moves the water. That's exactly what's happening with the wind. And these are surface currents that happen as a result of wind, primarily just wind. So you can see the blue coming towards the equator and the warm red coming from the equator towards the poles. So the Coriolis effect, before we get into deep currents, we need to talk about the Coriolis effect because, as you noticed in the last diagram, there's lots of curves. Why doesn't it just go from the pole straight up to the equator? Well, Earth is rotating and water is not stuck to Earth's surface. It floats above Earth's surface. And so surface currents are affected by the fact that the Earth is moving constantly. Surface currents in the northern hemisphere are deflected to the right as a result of the fact that Earth is moving, and in the southern hemisphere, they're deflected to the left. We're going to do a cool simulation on this to help you really. So here's a simple visual. So if you're standing on the equator and looking north, they move to the right. And if you're looking south, they move to the left. Super myth. Do toilets really flush the opposite way in the southern hemisphere? No, they do not. It's a myth. The Coriolis effect only affects large things that are not tightly bound to Earth's surface, like wind, water, airplanes. So pilots, they have to take the Coriolis effect into account whenever they fly an airplane. So they can't fly straight from one place to another. They have to, if they're in the northern hemisphere, veer their course to the right a little bit, and if they're in the southern, a little bit to the left. Now, of course, there's precise mathematical calculations. They're not just going a little to the right. They're precisely following specific directions based on where they're coming from and where they're going to. So gyres are circular ocean surface currents that form because of the Coriolis effect. So those are those circular things you noticed a couple diagrams back and that are about to come up again. So in the northern hemisphere, they go to the right, and right is clockwise. So you'll see surface currents in the northern hemisphere always spinning to the right, which is clockwise. And in the southern hemisphere, they'll always spin to the left, which is counterclockwise. And here is another example to show you that. So they will always spin to the right in the north above the equator, or to the left if you're below the equator. Pretty cool stuff. So the second kind of ocean current is density currents, or deep ocean currents. Water flows vertically when denser water sinks, okay? So denser water is colder water. It sinks and then spreads beneath the surface. The energy that drives these currents comes from the different density differences. Density currents are responsible for what's called the ocean conveyor belt. So the ocean conveyor belt cycles heat and salt throughout the whole world from deep water to the surface. So there's different temperatures. The deeper you go in the ocean, it gets colder. And there's different amounts of nutrients at different depths of the ocean. And so those different nutrients and different temperatures get cycled throughout the world with the ocean conveyor belt. And it affects weather all over the world. So deep water formation, you get to see up at the top of the diagram, the very top near the North Pole, you see deep water formation. So when the water is coming north from the equator, as it moves north toward the North Pole, the temperature is colder. So as the temperature gets colder, the temperature of the water gets colder, and then it starts to sink. As that starts to sink, it brings heat from the above and different nutrients from above below. And as you look around the diagram, anytime you see blue and red, like the border of blue and red, that's what's happening. It's really cool, and it's what's responsible for moving salt and nutrients and temperature around the world, which is responsible for all the weather across the whole Earth. Here's another diagram of ocean conveyor belt. This one's a little bit easier to look at. You can see it up at the North Pole on the left side of the screen, is in the Atlantic Ocean, as well as on the right side of the screen in the Pacific Ocean, and in the middle of the screen in the Indian Ocean. So there's 3 spots where you've got different temperature water. The top spot on the left and the right in the Atlantic and the Pacific is warm water. I'm sorry, just the Atlantic is warm water coming from the equator up, and then it gets cool and it sinks. The Indian Ocean is cool water coming up to the Indian Ocean. As it cools up, as it gets up to the Indian Ocean, it gets less warm. And so it's coming from below up to the top. And same thing with the Pacific. It's colder water coming from the South Pole up to the Pacific Ocean, and then it becomes warmer water. So the ocean conveyor belt never changes its shape, and it's caused by these 3 things. It's caused by the amount of salt at the equator, which is called salinity, and it's caused by changes in temperatures at the poles. The colder currents move along the ocean floor because cold water is more dense. All right, and things that affect water's density are these. These are really cool, and we're going to do a lab on salinity and density. So a decrease in temperature. When water becomes cold near the poles, it makes it heavier. An increase in salt. Salt makes water heavier. And when water evaporates a ton. So if you have high areas of evaporation, the water is evaporating, but the salt cannot evaporate with it. So it gets left behind, which makes that area saltier, which is going to make it more dense. Higher levels of evaporation equals saltier water and heavier water. So these are now 3 things affecting salinity. So we just talked about factors affecting density. Now what affects how much salt there is? So the formation of sea ice. Sea ice is fresh water, right? So fresh water absorbed, which makes the water underneath salty because salt can't freeze. And so the water freezes, and again, it leaves behind the salt, just like with evaporation. So anywhere that you have high levels of evaporation is going to be really salty. And anywhere that you have a lot of sea ice, the water underneath is going to be really salty and dense. And then precipitation runoff and the melting of sea ice. So when you have fresh water, precipitation is rain or snow or sleet or whatever, hail. Runoff is the water that's running off the surface of the earth into bodies of water. And then the melting of sea ice. Those three things are all fresh water. So when you have fresh water mixing with salt water, it's going to make it less salty. So the first two things make water more salty, and the third thing makes it less. Okay, upwelling. So upwelling, we talked about upwelling in 8th grade, and I think I did a pretty good job of drilling in your brains that upwelling is a good thing. So upwelling is when cold water rises from deeper layers to replace warmer surface water. Now, I just got done saying cold things do not rise because they're more dense. Cold water sinks. However, when you have enough wind that pushes the surface water over, it makes room for the colder water to rise, just based on pressure alone, pressure differences. So the wind blows the water over, cold water comes up from the deep ocean and rises vertically. With it, it brings nutrients from the deep, cold water to the surface, and those two things are perfect ingredients for fishing off the coast of North and South America. So this is, again, a really good thing because it allows it attracts all different kinds of fish and sea life that in turn help feed humans. Here's a nice diagram. So wind is blowing from offshore. It moves the water over, and water is going to replace it by moving up. Okay, we're getting there. Gulf Stream current. So the Atlantic Ocean current that originates in the Gulf of Mexico is the Gulf Stream current. And the Gulf Stream current is super duper important because it influences the climate off the east coast of North America, where we live, and the west coast of Europe, Great Britain. If we did not have the Gulf Stream current, we would have really cold temperatures. And we would have really cold temperatures because we wouldn't have this warm surface water off of our ocean to help influence the climates around us. So you've got the warm, fresh, less dense water moving north, okay? Got water moving north, the red. And then you've got it going down up at Greenland. So we've got warm surface water all along North America and to the western side of Europe. And then it goes up to Greenland and then sinks because the temperature up there is colder, saltier, denser, deep water. And that is the Gulf Stream current. And it does not change, and it's what's responsible for our weather. Here's another diagram of the Gulf Stream current. So if this current were somehow turned off, climates in all of the locations around the Gulf Stream current would be severely affected. This is just a really cool little tidbit. The Gulf Stream transports about 1.4 petawatts of heat, which is equivalent to 100 times the world energy demand, okay? Equivalent to 100 times the world energy demand. So underwater turbines that run off of energy from the heat difference in the density currents and the surface currents could technically be used to produce electricity equivalent to several power plants, which is really, really cool. There's so much energy there that's potentially available to produce electricity just like power plants would, just because of heat differences. All right, last part of the lesson. This is not on your guided note sheet. There's a little space on the bottom just to write it in. So tides. So the daily changes in the elevation of the ocean surface. So sea level is 0 meters. So 0 is sea level. So it's standing at the surface of the ocean is sea level. Tides change. They either come up higher onto the shore or they don't come up as high onto the shore. And they happen as a result of the gravitational attraction with the Earth and the Moon and the Sun. And so let's see, there's a diagram to explain. So in just a second, the diagram will come up, but when the Earth is closest to the Moon, it creates a tidal bulge because of the Earth-Moon gravitational pull. That bulge is called a high tide. It actually pulls the water. If you stood on the shore of the ocean for 24 hours, you'd see the tide rise and fall 2 times as a result of the fact that the moon's position changes daily. So here we have the moon and the earth, and then the green around the earth is illustrating the ocean. And so you see that it's pulling on either side of the earth. And on the top and the bottom, sort of, because it's tilted, on the top and the bottom, you see that the ocean is not as big. So those two places are low tide, the top and bottom, and the left and the right are high tide because of the moon's pull. So here's another diagram. The high tide side is caused by the pull of the moon on the Earth's oceans. The low tide side is caused by the pull of the moon on the mass of the Earth, pulling it away from the water on the opposite side. And last, you see that you have there's some different moon phases here. You've got the full moon on one side, the right-hand side, which causes a high tide, and then the top and the bottom are low tides. And then you've also got the new moon, which high tide, top and bottom low. And then you see where the sun is also. So the sun's always there. The moon is in different places because the moon is moving around Earth as the Earth is rotating and revolving around the sun. So there's lots of different movements going on that affect the gravitational pull. And that gravitational pull is what creates high tides and low tides. And you see the third quarter and the first quarter moon in the bottom part of the diagram. They create a different kind of pull. So you see the high tide and the low tide don't look quite that different. It almost looks like pretty similar ring of blue around the Earth. Whereas the top diagram, the new moon and the full moon have a bigger gravitational pull because you see that they're in line with the sun. So you have the sun, the new moon, the Earth, the full moon. Whereas the bottom diagram, you have the sun, and the sun's at a perpendicular angle, makes a T shape. So the sun and the Earth are in line, but then the moon, it makes a 90-degree angle. And so that has less of a gravitational pull compared to if they're in a straight line. Pretty cool stuff. So that was your lesson on oceans. And we're going to be doing some cool activities, investigations, labs to help you understand these things. Ocean currents, density differences between salinity and temperature, cool upwelling video clip that's on the website that you should watch, and Coriolis Effect simulation that we're going to do as shelf work. All right, I hope you all have a fantastic day or night whenever you're watching this, and we'll check in with you soon.